I'm Andrew Tolmack. I'm the program chair. It's a distinct pleasure to be able to introduce our invited speaker this morning. It's a cliche, but if there ever were a person who needs no introduction to this audience, it would be Guy Steele. In fact, I'm a little bit unclear what to say, so I thought I would just mention the following programming languages: Lisp, Scheme, C, Fortran, Java, Fortress. If you've had anything to do, any concern at all with the definition, implementation, or explanation of these languages, you owe a lot to Guy Steele. And we're excited to hear what he has to say about organizing functional code for parallel execution. Guy.
Good morning. Many of the ideas in this talk are not original with me, and I think that some of you in this distinguished audience are going to react by saying, "At last, Guy has seen the light." But I'm hoping that you'll find that this particular assemblage of ideas is useful to you. Another thing to tell you is that I'm going to be showing a lot of code during this talk. These are small examples. They will be typically 1 or 2 slides. There will not be time to read them all. Don't worry. Many of them represent ideas that are already familiar to you. And don't worry if you can't read every token of every declaration that's on the slide. Just relax and listen to the story. My big message is that with the advent of multi-cores, parallelism is now inescapable. It's been a research topic for the last 20, 30, 50 years. But we're now facing practical consequences on every laptop. Effective parallelism uses trees. Associative combining operators are good. MapReduce is good. Catamorphisms are good. There are systematic strategies for parallelizing superficially sequential code, and we'll be looking at some of those on later slides. And the last point, perhaps my most important point this morning, is that we must lose the accumulator paradigm and emphasize divide and conquer. Again, old ideas, but I think they have a new urgency in today's multi-core world. This talk is about performance. The bag of programming tricks that has served us so well for the last 50 years is now the wrong way to think and must be thrown out. That's my big message for today. Later, I will temper this rather hyperbolic claim, but I want you to keep this in mind for the next 50 minutes. Why do I think we need to get rid of the old programming tricks? Well, it's because there's a big difference between good parallel code and good sequential code. Good sequential code minimizes the total number of operations because the total number of operations is strongly correlated with delay in sequential code. You use clever tricks that you can reuse previously computed results. But good parallel code will often perform redundant operations because there's a trade-off between computation and communication. And sometimes you're better off expending extra computational effort in order to reduce the communication effort. Also, good sequential algorithms minimize space usage. They use clever tricks to reuse storage. But good parallel code often requires the use of extra space to permit temporal decoupling. Now, these things have to do with the efficiency of the computer, and I want to talk about the efficiency of the programmer. Sequential idioms stress a linear problem decomposition. You process one thing at a time and accumulate results. And I think we need a different mindset. Good parallel code usually requires multi-way problem decomposition and a multi-way aggregation of results. And this style of programming just organizes code in a very different way from the typical sequential style, whether it is imperative or functional. So let's look at some code. Let's add a bunch of numbers. Okay, so here's a typical Fortran style do loop to add up a bunch of numbers. Can it be parallelized? Who cares? It's got a bug in it. I forgot to set sum to 0. This is one of the things that really bugs me about a lot of sequential languages, is that it's very easy to forget to initialize the accumulator. Okay, now can this code be parallelized? Well, it can be, but the way I've organized this code is already bad, and we've known for 30, 40 years that good parallelizing Fortran compilers look at this code and say, oh, I know what he's really trying to do. He doesn't want to make a central accumulator bottleneck and then have all the different threads bang on that one sum variable. We need to turn this into some kind of distributed computation, and then we'll sum the results at the end after we sum them in batches. And people like Fran Allen have made a career out of trying to figure out how to take sequential code like this and turn it into what it really ought to be on a parallel computer. Now, what does a mathematician say when he or she wants to add up a bunch of numbers? Well, there's this big sigma notation, which is very convenient. And you can either control the index variable from I going from 1 to a million, or maybe you just say big sigma of x. And Fortran 90 has a simple sum primitive where you just hand it the array and it hands you back the sum. This kind of notation is good because it says what you want to do without a commitment to how. So there's no commitment to strategy. This gives a good compiler or a good interpreter implementation some wiggle room to figure out the best way to carry this out. Now, let's consider the computation trees that are described by programs that add up a bunch of numbers. So here is the sequential loop, and we set sum to 0, and then we add in these things one at a time. And if we take away all of the machinery that runs the do loop and just look at the additions that are happening in order to compute the sum, we find that we have described a computation tree that looks like this. And it's a binary tree, but notice that it has this long left spine. And therefore, there is a delay of 1 million in actually doing all these additions because they must be done one at a time. Now, one way to parallelize this is to say that we'd really like the do loop to be done in parallel. So we slap a parallel keyword on the do loop. And as a result, introduce another bug. There's a race condition now. If all of the iterations of the body can be done in parallel, then they can all fetch x sub I, all fetch sum, do their additions, and then they all try to store, and some of the additions can be lost. So this is bad. So the way you fix this is by marking the body atomic. And that's all very well, but we haven't really solved the problem. This says that the bodies may be done in any order, but they have to be done in some order. And as a result, we still get this long left spine. So it may be that the x's get added in some order other than in sequential order from 1 to a million. We've still got this long left spine. This is a sequential algorithm, in effect. What kind of computation tree would we really like to see? We'd really like to see something more like this balanced binary tree here. But the real question is, what sort of code should we write to get a computation tree of this shape that will do the same amount of work, but because of the potential to do it in parallel, the delay may be log time rather than linear? What sort of code would we like to write to describe this kind of tree? Well, the obvious answer, at least at this conference, is we'd like to write functional code. But that isn't the complete answer to the story, because just writing your code in a functional style rather than imperative won't necessarily get rid of the long left spine in the tree. So now let's look at this diagram. This shows a Lisp list. By the way, I'm going to be jumping back and forth among different programming languages because I like them all. And I'll try to notify you when I've changed syntax. Okay, so this is Lisp code. And this is the standard definition of length on a list. It's a recursive definition. And the total work that performs is linear in the length of the list. And the delay is also linear in the length of the list because you don't have any choice. You're given one pointer and you have to chase down one pointer after another. The problem here is that linearly linked lists are inherently sequential. Compare this to the definition of arithmetic using the piano axioms. The number 5 is conceived of as being start with 0, then add 1, then add 1, then add 1, then add 1, then add 1. That's just like a linked list when you're trying to decompose that again. Binary arithmetic is much more efficient than unary because it doesn't compose a number one at a time. Instead, you start with an integer and you divide it in half. And maybe you've got one left over and that becomes the low order bit. And then you divide it in half again by repeatedly dividing in half. We get a binary bit string rather than this unary length piano arithmetic description of an integer. And in fact, in real hardware processors, we apply the trick twice. We repeatedly divide integers in half to get a bit string, and then we take those bit strings and divide them in half and build carry-save adders so that the amount of time it takes to do an addition is actually logarithmic in the length of the bit string, or log in the value of the integer. So this idea of doing binary decomposition rather than linear unary decomposition is very important. And for lists as well, we need a multi-way decomposition paradigm. And again, this is not new. You've seen this in numerous papers before. The way we define length on a list is to consider the 0 case, the length of the empty list is 0. The 1 case, the length of the singleton list is 1. And otherwise, we can take the list and divide it into two pieces, take the lengths of each piece separately, and then add those together. So this is really just a summation problem after all. Now this has, the total work here is also linear in the length of the list, but the delay might be linear, but it might be log depending on exactly how you do that split operation in the third clause there. It might even be worse than linear if splitting has worse than constant cost. But if we can keep the splits constant time, and if we can do the splits cleverly, then we may be able to get away with only a log time delay. So this is good. So this suggests a different representation for lists, and so I'm going to introduce conc lists here. Again, this should be a familiar idea to you. Instead of having a representation for null, the empty list, and then adding on one more thing to a list the way we do in Lisp, we're going to have a representation for the empty list, a representation for singleton lists, and then a way to concatenate two lists. So the double box looks very much like the one we use in Lisp, except that instead of putting a single line down the middle, I put a double line to remind you that it represents concatenation. And using this representation, we can represent a list of 4 numbers, 23, 47, 18, and 11, by using this balanced binary tree form. And this represents 4 singleton lists, and then I have concatenated them pairwise and then concatenated those. And so that is a representation of this linear list, 23, 47, 18, 11. But there are other ways that I could represent this list as well. For example, I could use this long left spine sort of list if I chose to. And I might have reasons for doing that. And the expression that describes this tree structure is shown over there on the right. Or here's a possible third one. Here I've chosen to use null lists down at the bottom purely for the sake of demonstration. They just can be there. And here's a fourth one. In fact, this one looks very much like a Lisp list with a null at the end and the cars of the list being readily available as I go down it. Now this is a redundant representation. In Lisp, given a tree structure, there's only one box and pointer diagram that will represent that tree structure. But here there are several different conch trees that will represent the same conceptual list. So in fact, it takes more bits to represent a list in this style. But there is value in this redundancy. This redundancy gives us some wiggle room in the implementation to use different trees of different shapes for different purposes to represent the same logical data structure. Compare this with garbage collection, in which many different bit patterns in storage can represent the same list. And this gives the garbage collector some wiggle room to organize storage under the table and manage it in appropriate ways. So it can choose the relevant bit patterns. It can choose to optimize for other qualities, such as locality. We are going to use conch trees to optimize delay. Okay, so here's a comparison of cons lists and conch lists in terms of language primitives that you might use as constructors for lists and predicates and accessors. So for cons lists, we have the empty list, shown as quote open close, and we have this constructor cons. And for each of these 2 sub-data structures, we have, well, for one of them, we have a predicate. Null question mark tells you whether you've got an empty list in hand, and if not, then it must be the other case. And for cons, we have these accessors, car and cdr. And then there's an algebra that describes some relationships among these different primitives. In particular, an important one is that given a list x's, then if you take its car and you take its cdr and you cons them back together, you get the same list. In the case of conch lists, we have the 3 primitives instead of 2, the empty list, a way to make singletons, and a way to concatenate 2 lists. There are predicates null and singleton. If we have a singleton list in hand, the accessor item will give us the goodie in it. And then for conchs, we have left and right. And we have a very similar algebra down there at the bottom. The list of item of s is equal to s. And if we take the left and the right of a conch and then conch them back together, we get the same list back. Now, one can use these accessors left and right. As a matter of style, I prefer to replace them with a single accessor I call split, which is a functional. It takes a function as its second argument, and it calls that function, think of it as a continuation, on the left list and the right list. And I do this just to sort of mentally keep the left and the right together. This also, if I choose to use a side effecty implementation, allows me to play games under the table of reorganizing or rebalancing conch lists in an invisible way. And when I split it, I get a particular split of that list, but if I call split again, I might get a different split. I just point that out as an implementation option. In fact, I'm not going to take advantage of it during the rest of the talk. And for the purposes of this talk, you can think of split as, in fact, being purely functional, as always giving you the same split every time you call it. Okay, I'd also like to point out that while we often call split with a lambda expression, it is just a functional, and so you get this very nice algebraic expression, split x's conch equals x's, down there at the bottom. Okay, now that we have these primitives, we've got one set of primitives, car, cdr, cons on the one hand, and we've got item and list and conch and split on the other. Now we're going to look at using those as basic primitives for defining a number of operations on lists. Okay, so this first slide should be completely familiar to you. This is defining first, rest, append, add left, and add right in terms of car, cdr, cons. And this is an elementary exercise. And the thing I just want to point out here is that first and rest can be defined in constant time in terms of car and cdr. Not at all surprising. Append is linear in the length of the first argument in the way that it's customarily defined. And that's something that a good Lisp programmer needs to know, that it's linear in the first argument and constant time in the second argument. If you aren't aware of that, you can write Lisp programs that have very bad execution times. Add left is constant time, but add right is linear time in the length of the x's, because you have to chase down to the end to figure out where to stick in that thing on the right. Okay, now let's compare that with defining lists in this balanced form using item, list, split, and conc. First is no longer a constant time. In principle, you've got to search down that tree, the left-hand spine of the tree. If the tree is nicely balanced, that will be logarithmic time. If it's badly balanced, it could be linear time, but it depends on the depth of the left path. Similarly, taking the rest of the list requires taking the depth of the left path. And notice that first and rest are in effect, first is chasing down the left spine. Rest is in effect constructing a new tree if necessary. It uses append in that last clause. Append, on the other hand, instead of being linear in the first argument, can be done in constant time. Pretty much all you have to do is call conc. But there's an option here. Instead of simply calling conc, look at the last line of this code. We might call conc and then call some routine called rebalance. And rebalance might take some effort to try to make the tree, keep the tree relatively balanced so that on average, first and rest will be log time at the expense of making append perhaps non-constant or perhaps constant but somewhat longer than it would have been otherwise. So there's an opportunity here. And this is exactly why we wanted the redundant representation. Now, add left and add right can similarly be written in this structural recursion decomposition way. We can consider the separate cases of add left to a null list, add left to a singleton list, and add left to a conc list. But in fact, it's easier just to define them in terms of append and let append do its job. So to add left, we simply make a singleton list of A and then append that to the X's. And similarly for add right. Okay, now we get to the meat of the matter. Now we have some really interesting primitives. Let's look at map, reduce, and map reduce using car, coulter, and cons. Well, map is what back in the olden days we called map car. It just takes a function, applies it to each element of a list, gives you a list of the results. So if we map the square function down 1, 2, 3, we get 1, 4, 9. Similarly, we can take reduce and feed it a list and give it the functions plus and the identity for plus, which is 0. It will add up all the numbers and give us 14. More interestingly, we can combine these two things into a single function called map reduce that does both jobs at once. And the definition shown on this slide should be completely familiar to those of you who have played with these functions at all. And each of these functions is linear in the length of the argument x's. This is discounting the amount of time actually taken by the functionals f and g that it's applying, which is the mechanics of doing map and reduce down a list is linear. In terms of map reduce, we can then define other operations such as length and filter. To find the length of a list, we simply map each element into a 1 and then add up all the 1s, and we get a linear time implementation of length. That's nice. There are several ways we can do filter. We could do filter using the structural recursion approach, looking at the 3 separate cases of the empty list, the singleton list, and, there are 2 cases, the empty list and cons list, and for conses, there are 2 cases. It looks like we've got a 3-case con, which really only 2 cases of structural recursion. So if the list is not empty, then we look at the first thing, check the predicate on it, and then there are 2 cases to consider whether we want to include the item in the result or not. That's linear time. Now, an old idiom is instead simply to map the predicate down the list, producing either a singleton list or an empty list, and then applying append to the resulting list. This apply of a function such as append or plus is an ancient idiom in Lisp and works because many of the functions such as append and plus were defined to take any number of arguments in just one. Unfortunately, we're not really sure in what order those arguments are given to appends, so we're really not quite sure what the execution time is for this second definition of filter. If we apply it in the right order, it might be linear. If in the wrong order, it might be quadratic, depending on whether we left associated or right associated the arguments and feeding them to append. Now, in this last definition, I've called map reduce instead, and it is in fact linear in the length of the x's in execution time. But I know that only by doing a deep analysis, looking at the precise definition of map reduce, and determining that in fact each time it calls append, its first argument is of length 1. And therefore the call to append will take constant time, and therefore the call to map reduce overall will take linear time. That requires a deep analysis. Finally, let's take a look at reverse. If we define reverse in the obvious way using structural recursion, then we end up using something like add right, and reverse takes quadratic execution time. This is another bugaboo of Lisp programming. And one of the things a Lisp programmer learns early on is that reverse is a special case that requires a trick. What you really do is define a function called revappend, and then you feed it the thing you wanted to reverse and an empty list, and it accumulates, it tears apart the first list and accumulates values onto the second list, and that's how you get reverse done in linear time rather than quadratic. Okay, so I've shown you a bunch of sequential definitions of various functions on lists using Carr-Cutter and cons. Now let's look at what this might look like using item list split and conc, which gives us some potential for parallelism. Here's a definition of MapReduce, and let's take a little more time to look at this. It uses structural recursion, and it looks at the three cases of an empty list, a singleton list, and a conc list. And if it is a null list, it applies the identity function, returns the identity there. If it's a singleton list, then it grabs the item and applies f to it. Otherwise, it splits the list into two pieces, calls MapReduce on each of those two pieces, and then combines the result using G. Now, there are two interesting things to note about this definition. One is that MapReduce, in addition to the list x's, takes three things, f, g, and an identity value. And each of the three cases of the cond uses one of those three values, so that there's a correspondence between the catamorphism that we supplied to MapReduce and the pieces of the structural recursion. That correspondence was not apparent in the Carr-Cutter cons version of MapReduce. The second thing to point out is that because we have split the list into two pieces and we have two calls to MapReduce, two recursive calls to MapReduce instead of one, we have an opportunity for parallelism if we can make those two calls to MapReduce independently and in parallel. Then in terms of MapReduce, we can easily define map and reduce, and you see those here. Now, once we have MapReduce defined, it's very easy to define functions such as length, filter, and reverse. Length simply, in fact, is the same definition we saw before in the serial case, and that's why MapReduce is such a nice abstraction. Similarly, filter is easily done by feeding it a function that uses the predicate to map singleton items onto either a singleton list or the empty list, and then uses append as the reduction operator. Because append in the parallel world is constant time, or approximately constant time, then we can do this in overall logarithmic time if the MapReduce is logarithmic. In fact, even if the append takes logarithmic time, the overall execution time will still be logarithmic in the length of the x's. And finally, reverse is completely straightforward. Notice that the combining function takes, there's a typo here, it's got yx to be ys. It takes y's and z's and then appends the z's to the y's. And that's how the reverse will happen. Reverse is also logarithmic time. Okay, so now that I've given you some finger exercises in this, here's a more interesting exercise, writing merge sort and split and quick sort in terms of these binary split lists. And I'm not actually going to show you the code for this. This is an exercise to the reader. Do it offline. You don't have time to do it now while I plow through all these slides. But it's interesting to note there's a symmetry between quicksort and merge sort. Quicksort, in effect, does structural induction on the output. It takes a list, does a careful partitioning of the list into two lower and upper halves. This part is tricky. Then it recursively sorts the two halves, and then cheaply appends the two sorted sublists. You can use conc for that. Merge sort is just the opposite. It does structural induction on the input. You do a cheap split of the input into half, recursively sort the two halves, but then you've got this problem of carefully combining two lists and maintaining their sorted order. That part is tricky. But there is a sort of a correspondence here. Okay, now I'm going to show you several more definitions of the filter function, and I'm going to change notation here again. I'm going to use the Fortress language that my research team has been developing at Sun. And three things about the Fortress language are that we've designed it to be very user extensible. So for example, we use operator overloading very heavily and rely on users to use it tastefully and conscientiously. To this end, we support not just the ASCII character set, but the Unicode character set. We've made all the correct symbols available. Please use them. In fact, overall, we tried to make the flavor of the notation very mathematical in style. And I hope that some of that flavor will come through on the next few slides. And finally, there's an emphasis on parallelism. In particular, if you have a binary operator, the two operands may be evaluated in parallel. And we have an interpreter that does that, and we're working on a compiler. So we'll go through this code at a little more leisure. We have a sequential implementation of filter. It is parameterized by a type parameter E, and it takes two arguments, the predicate and the list x's. The predicate maps e's onto booleans, and the x's is a list of e's, and it returns a list of e's. And the first thing we do is we initialize an accumulator called result, which is a list of e's, to the empty list. and then we are going to accumulate things into the result. We use this for loop, and A takes on successive values from the list. The little function seq means we intend to traverse the list sequentially rather than in parallel. So traversing the list sequentially, we test each item A with a predicate P, and if the predicate is true, then we use add right to stick the value into the result. And when we're all done, then we return the result, as shown there just before the end keyword, that last end keyword. Here's an example of use. If I define a function odd, which can take any integer x, notice the use of Blackboard Z for the integer data type, and by that I mean big nums. Then it simply takes x mod 2 and sees whether that's non-zero. And given this predicate odd, we can call sequential filter on odd and this list of integers 1, 4, 7, 2, 5, 3, and we expect to get a list back out that contains just the odd numbers, preserving the order in the original list. Okay, so that works fine. Here's a recursive definition of the same filter function. This uses structural recursion. If the x's passes the is empty predicate, then we produce an empty list. And otherwise, we call the extract left method of x's and then for the get method on that. Don't worry about why I need two method calls there. It has to do with the use of the maybe type by extract left, if you're familiar with that. We know in this case that we've already tested to see whether it's empty, so we will get first and arrest back. And the extract left get method returns a pair of the first and the rest, which are then, and the variables first and rest are then bound to that up there. Then we compute rest prime by calling recursive filter recursively. And now we test the first item, and if the predicate is true, then we add it onto the left of rest prime, and otherwise we return rest prime. So notice this is adding things onto the left rather than adding things onto the right, but it's still in an accumulative paradigm. Still has linear time delay. Here's a parallel version of it. This time I'm using a different strategy for finding out whether the list is empty. I could have used either in either definition. But here I've chosen to look at the length of a list. The vertical bars are a way of asking for the length of a list. So if the length of x is 0, then I return the empty list. If the length of x is 1, then I use extract left to find its item x and then use the predicate and construct either a singleton list or an empty list. This business of producing either a singleton list or an empty list in response to a predicate is a very common idiom in this style of programming. It takes some getting used to. Finally, if x's is a list of length 2 or more, then we split it and call the two pieces x and y, and then call parallel filter on x and parallel filter on y. And that is an opportunity for parallelism because the two operands of the concatenate operator there may be evaluated in parallel. When we get the answers back, we concatenate them with that double vertical bar. Now, this is exactly the same code. I've just done a little color coding here, and I'll point it out with a laser pointer. You will notice that up here there's an empty list, and down here is the concatenate operator, and then here is this if-then-else statement that uses the predicate. Everything else remaining is simply standard boilerplate for the structural recursion on a list and applying a catamorphism and putting it back together. That boilerplate is such a common pattern it's worth capturing with special syntax. And so we do that in Fortress, and we can write it this way instead using a reduction operator. We can simply say, as x is drawn from x's, we apply the blue code, if p of x then singleton list of x else empty list. And then we apply the big concat operator the same way we would apply big sigma to do a summation, or big max to take the maximum or the values. Here we apply big concat to concatenate all of these lists, which are either singletons or null lists. And so this provides an implementation of the filter function. And so this very concisely provides for an automatic implementation of that generator boilerplate that takes a list, generates the elements, executes a body for each element, and then puts the results back together. And actually, filters are so useful that, in fact, they're built into Fortress comprehension notation in the usual way. So an implementation of the same filter operation using a list comprehension is to simply say, give me back a list of the x's, give me back a list of values x such that x is drawn from the x's and x satisfies the predicate p. Oh, and by the way, in Fortress, just as we can use big concat, we can use big sigma and big max, and we can have the i's going from 1 to a million, or we can simply draw a from x and say big sigma of a, or you can just apply big sigma to the list to begin with. All of these notations are possible in Fortress. They all work. Okay, now I'd like to talk a little bit about order. I have a point of order here. For filter, unlike summation, we depend on maintaining the original order of the elements in the input list. So note that both concatenation and addition are associative, but only addition is commutative of those two. It's important not to confuse the ordering of the elements in the result list, which is a spatial order, with the order in which they are computed, which is a temporal order. It's very easy to get confused and say, I want to do everything in parallel. I don't care in which order it gets done. Therefore, I better use a commutative combining operator, because commutativity is what says the order doesn't matter. No, we're talking about two different kinds of ordering here. Commutativity has to do with the spatial ordering in the result, the logical ordering within the logical data structure of a sequence. That's a completely different ordering from the temporal ordering in which things get computed. Sequential programming often ties the one to the other. We're used to those two orders being conflated. Good parallel programming decouples this unnecessary dependency. And I want to point out that the strategy for parallelism I'm discussing in this talk relies only on associativity and not commutativity. So it's okay to use operators like concat that are only associative. And this is a source of great power. Now here's another important but powerful idea. The idea of conjugate transforms on data. The idea is instead of doing computation within a data type T, instead you map things over to some other data type U, do the computing there, and then project the result back. More specifically, instead of mapping input items directly to an output data type T in a computation, you map the inputs to a richer data type U, possibly by way of T or possibly directly. Perform the computations in the richer space U. Typically, U is redundant so as to make the computation simpler to express or to make it faster, or both. And finally, you project the result from U back into T. So here's an exemplar of that, the three-way unshuffle problem. The goal is that you are given a deck of cards and you want to deal it out into three piles, round robin. So for example, here's an example. Given the list of letters from A to K, we want to produce the list of A, D, G, J, B, E, H, K, and C, F, I. Notice that these three result lists aren't necessarily the same length. And they won't be if the length of the input list is not a multiple of 3. Okay, well, I think all of you know how to write some kind of sequential code to do that. You take the three piles and you deal them out one at a time. And there are various ways of organizing that in either imperative or functional code. But let's try doing it using a divide and conquer approach. We're going to take the list and keep repeatedly divide it in half till we get down to the singleton cases. So the base case is that if you have an empty deck, you're going to get 3 empty piles. And if you have a singleton deck, you're going to get a singleton pile and 2 empty piles. Now, how can we combine those result piles into bigger piles? Well, let's work an example. Let's consider the input A, B, C, D. We'll split it in half to make A, B, and C, D, and then split those further. When we get the singleton piles for A and B, we will want to get a singleton pile of A, a singleton pile of B, and a null list, and similarly for C and D. Now, the next step is a little more puzzling, but when we work with it, we find that we've got 3 piles here, and we've got 3 piles here, and we're going to concatenate the 3 piles in some order. We just need to figure out the correct correspondence. And so here's a piece of Fortress code that does that. And it follows this structural recursion strategy. For the empty list, we produce 3 empty lists. For the singleton list, we produce that singleton list and 2 empty lists. Otherwise, we split the list, call unshuffle recursively to get 2 triples, A, B, C, and D, E, F. And now there are 3 possible ways to match them up. And it turns out that if you compare the length of C to the length of A and then the length of B to the length of A, that will tell you what the correct correspondence is. Unfortunately, these tests are slow. To find the length of a list represented in this tree style takes some time. It takes linear work and it takes at least logarithmic delay. So we're going to speed up this code by using a conjugate transform into a richer data space. Instead of computing on 3 tuples, we're going to compute on 4 tuples. And so I've made this function unshuffle prime, which operates on 4 tuples. Let's look at, no, let's not. Okay, so unshuffle will take this list X's, and if the list is empty, it'll produce 3 empty piles and a 0, indicating that the total amount of stuff in those piles is 0. So we're essentially going to keep track of the length of the list, mod 3. And in the singleton case, we'll produce X's, 2 empty piles, and a 1, indicating that the total amount of stuff in the piles is 1. Otherwise, we split, call unshuffle prime recursively, getting back to 4 tuples. And now we use J, which came back with the first triple, to tell us what is the amount of stuff in those 3 piles, mod 3. And doing a case analysis on J tells us the correct way to match things up. And the fourth thing in the resulting 4 tuple has to be J plus K mod 3. And then finally, the definition of unshuffle calls unshuffle prime on the x's, gets back a 4 tuple, projects that back into the desired 3 tuple space simply by dropping the last item. And in this way, we manage to solve the unshuffle problem in a way that takes linear total work and potentially only logarithmic delay. Now, another thing we can do is take, I'm going to back up a slide again. I want to draw your attention to these 6 lines of code here. The recursive call to unshuffle, and it's getting back 2 4 tuples, and then this case analysis on J. Let's extract that as a binary operator on 4 tuples, and I will call that box plus. So box plus takes 2 4 tuples and does this case analysis and returns a new 4 tuple. And once I have defined that combining operator, I can then define unshuffle very concisely by saying that its job is for every x in the given list x's, produce an appropriate 4 tuple for that singleton base case, and then apply big box plus, and big box plus does the job full. This is a very eye-opening style of programming, and I found that it changed my approach to sequential programming as well. I found that now that I've become sensitized to the idea of mapping little cases into solution spaces and then combining solutions, that I find myself noticing when I do something else in my sequential code. Every time I initialize an accumulator, I say, ooh, did I really want to do it that way? It's an interesting style of programming. Okay, now I'd like to take a look at merge sort. I'm going to show you this slide, back up a slide. We abstracted the combining operator for unshuffle as box plus and then used a big box plus. Similarly, for the merge sort problem, we can abstract merging of 2 sorted lists as an operator I will call merge, instead of choosing a symbol, and then use big merge. So if we define an operator merge that takes 2 sorted lists and produces a new sorted list, notice that this operator is associative and has the empty list as its identity. Thus, sorted lists under this merge operator form a monoid. Therefore, we can implement merge sort as simply saying, for each x in x's, map x to the singleton list, do big merge. Boom, you're done. Quick sort is a little harder to find that way because it does structural recursion on the output rather than the input. Because merge sort is doing structural recursion on the input, we can use this style. Okay, now I'd like to show you some definitions of implementations of the parallel prefix problem. The goal is, given a list, to produce the running totals of that list and the final sum of the sequence. So, for example, I've shown this to you in symbolic form and also given you a numerical example. Some formulations of parallel prefix hand you back only the list and not also the final sum, but this will be a convenient formulation for our purposes. And I'd like to note that parallel prefix is useful with any monoid. For simplicity, for these examples, we restrict our attention to addition on integers. But parallel prefix is useful with operations that are not commutative, and that's worth pointing out. So here's one way of defining it in Fortress. This is the straightforward mathematical definition. We have a list comprehension using big sigma on subsequences of the list x's. Unfortunately, defining it this way produces total work that's quadratic in the length of the list. So forget that. Here's a fairly straightforward recursive definition of the structural recursion sort we've seen before. And we have the 2 base cases. Note that when I say x's sub 0, that returns the sole item of the list x's. And we recursively call pp sum, call the result p's and q's. And then we concatenate the p's to the q's. We have to adjust the q's by grabbing the sum of the p's, which is given as a, and adding that to each element on the right. Now the total work is linear rather than quadratic. Unfortunately, this dependency on a of computing the right half of the result, in the recursive case, results in a delay that's at least log n squared. We'd like to do better than that. Okay, so instead of using a value we got back from recursive call to pp sum, instead we're going to try handing the value to be added in from the top. So this version of pp sum calls pp sum prime and hands it x's and also 0, which is the value by which to update things down inside of it. And we'll keep repassing k down. And in this recursive case, notice that when we call pp sum prime, on the left half we hand it k, and when we call it on the right hand side to take the parallel prefix of the z's, we hand it a. Unfortunately, a did come out of the result of the first call to pp sum prime. So we still have a dependency on a The total work is linear in x's, and in fact, its dependency on a in this formulation results in a linear time array rather than a log squared time delay. So that's no fun. However, this idea of passing down from the top, a value down from the top, turns out to be the right idea in the end, but we need a trick first. Before we look at that trick, let's look at another piece of code. This code is written in Nestle, yet another programming language. I swiped this from Guy Block's 2009 PPOP slides. And this is a very clever idea. The idea is that to take a parallel prefix of a list, you take the elements of the list in pairs, sum them, so as to make its length, cut its length in half, take the parallel prefix of that recursively, and then use that resulting parallel prefix values to do some adjustment at the end, fixing it up at the bottom, and then you do this interleave operation. Now, Nestle uses a sort of array representation to represent nested vectors. If we use our tree representation for the lists and use this algorithm, linear time total work is expected. The delay is still log n squared. Can we do better? Well, I'm going to borrow yet another idea, the idea of monoid cached trees. And this is an idea I ran across in this paper on finger trees by Hinz and Patterson. And there are a lot of good ideas in this paper. Finger trees are a much richer data structure than you will see from just looking at my slide here. I advise you to go read the paper. But I'm going to grab just one idea from that paper, the idea of taking a tree and annotating it with values from a monoid. And so we're going to add an extra item onto our empty node, our singleton node, and our conc node, and I'll call these empty leaf and node. And here on the left you can see a tree that has cached sums. Just for each singleton item, I've duplicated its value and then propagated the sums up the tree, and so we have the sum available at every subtree. On the right, we have a tree with cached lengths. You can cache any sort of monoid. Notice that keeping track of the leftmost leaf or the rightmost leaf or the maximum value, these are all monoids, and therefore easily cached in this style. Here's Fortress code that declares the necessary data structures. This is not terribly interesting, except to point out that the common trait, which is inherited by all of these objects down here, empty leaf and node, declares an abstract access or value, which is then implemented by each of the objects. So there's this val field type V. And now if we use this data structure to implement the parallel prefix problem, we end up with a solution of roughly the following form. To compute a parallel prefix sum, we take the given list x's and feed it to the sum cache routine, whose job is merely to make a copy of the list, but cache the sums of the subtree up the tree. The result is C. Then we had C to PP finish and hand in a 0 from above. And so that 0 will be added to every element of the resulting parallel prefix calculation in addition to what it calculates. And by the way, C caches all the sums, so C.val is the desired sum over the entire tree already. Sum cache is just really the obvious structural recursion, and that is where it is propagating the monoid up the tree. And the job of PP finish is simply to do the two base cases in a straightforward way. And the interesting thing happens down here. When we do PP finish on a node, we call it recursively on the left part, handing down k, and we call it recursively on the right part, and we hand it k plus n.left.val. And that is the important point. We have used the monoid caching to cache the sum of the left-hand subtree so that we can access it in constant time rather than requiring logarithmic time or worse. And it's the fact that that access is constant time that makes the overall algorithm have delay only log n instead of log of n squared. So the monoid caching has saved us a log n factor. After playing with these algorithms, I have stumbled across a combination of operations that reminds me of MapReduce, and I call this MapScanZip. Please think of a better name. This is not very euphonious. In particular, if you spell it all lowercase, it looks like maps can zip, which is not what I had in mind. I want a map, a parallel prefix, and a zip. But the point is that monoid cached trees provide a particularly fast implementation of this combined operation, and also has the advantage that it gets the individual elements of the result close to the original inputs. This matters if you're using some kind of distributed data representation and you're trying to maintain locality. Notice that zip is difficult in the general case of tree-structured representations of lists because the shapes of the trees might not match. This is related to the old same fringe problem that people worried about 30, 40 years ago in in artificial intelligence laboratories trying to compare the fringes of two tree-represented lists. If the shapes of the trees don't match, then zipping them is hard. But in this case, it's very easy, and so building it as a single primitive may be useful. Okay, my last big program example has to do with splitting a string into words. So I like this example because it's completely non-numerical in nature and may have applications. It reminds people more of databases than scientific computations. But it's still a toy example. Given a string, divide it up into its words. And for the purposes of this example, we'll assume we're dealing with strings containing only letters and spaces. Words must be non-empty. Words may be separated by more than one space. There's no such thing as an empty word. If you've got two spaces in a row, that counts as a single word separator. And the string may or may not begin with or end with spaces. So using good test-driven development, I've developed some tests here for the code. So given the string, this is a sample. We expect to get a list of 4 words. This is a sample. Here is another sample. I've got things sort of extra spaced out. I still get only 4 words back. There might be just one word, and there are some empty cases of interest. Okay, now I think all of you know how to write a fairly straightforward sequential code for this algorithm, and here it is. Given the string S, which we are to split into words, well, the result is going to be a list of words, so I better set up an accumulator. So here's this accumulator called result. And furthermore, in the course of accumulating words, I need to find the words, so I need to accumulate the characters of a word into a word, so I'm going to need a second accumulator. I will call that word, and I'll initialize it to an empty string. And now, as this for loop goes sequentially through the string, we take one character after another and see whether the character is blank or not. If it's blank, then we separated a word, and we need to see whether, in fact, we've got a word. So if the word is a non-empty string, then we need to accumulate it onto the result. And in any case, we reset the word to be the empty string. If we found a letter, then that letter needs to be concatenated onto the word accumulator down there. And we do this until we come to the end of the string. And now we've got a list of words and a result. But there also might be a partial word, which is now known to be a complete word, accumulated into the word accumulator. So we need this fix-up computation. We need to check word one more time. If it's not empty, stick it onto the result. And finally, return the result. So this is a double accumulator sequential implementation of this problem. Now let's look at doing it in parallel. Instead of thinking about marching through the string in order, we're going to think about what it looks like to take substrings and produce subsolutions of the problem. So here I've taken a string and chopped it into 4 pieces. If it turns out that a piece of the string is all letters, I'm simply going to represent that as a data structure called chunk. So you can see sesquipeda has become a chunk. If a stretch of the string contains a space, then I'm going to use a different structure called a segment to represent it. And the segment simply is a list of all the words that can be found in there, possibly a chunk on the left and possibly a chunk on the right, representing partial words that might need further gluing onto once we know more of our context. And so you can see up there a segment beginning with the word here. We don't know yet that there's nothing more off to the left of the string. And for sure there are 2 words, is and and then there's a word break. There's a segment there consisting of Leon and Strin. We know there's an empty list of words in the middle, and we've got 2 chunks that might need gluing on either side, and so on. Okay, given this chunk and segment data structures, how do we glue things together? Well, what we're going to do, first of all, is to map the single characters into base cases. So letters will get turned into singleton chunks, and spaces will get turned to segments that have no words and empty chunks. And here's the code. We're going to zoom through this. We need a utility function called maybeword that checks to see whether a string is empty or not and produces either the empty list or a singleton list, that common filter idiom. We're going to define a trait word state, which comprises chunk and segment. And notice this interesting declaration. It extends associative of word state and circle plus. This is something I've elided in my earlier examples, but in Fortress you can explicitly declare an operator in the type system to be associative. And while we don't have a theorem prover yet that will check that, we do use unit testing, and there's an automated unit testing facility that will run this over test data and make sure that the operator behaves associatively. And then here's the declaration of the operator circle plus. Now let's look at the implementations of circle plus. Here's the definition of the object chunk. It has one field named S, which is a string. And we have to cover the case of combining a chunk with another chunk and then combining a chunk with another segment, and there are the necessary concatenations and data manipulations. We're not going to go into the details. Here are similarly, given a segment, we need to be able to combine the segment with a chunk or the segment with another segment. And again, there are concatenations. And when we combine the right chunk in that last line, the right chunk of the left segment, with the left chunk of the right segment, we need to use maybe word to see whether there's really a word there or not, and concatenating that into the list of words in the center. Okay, now we have this thing process char that takes care of the base case. It checks to see whether C is a blank, and if it's non-blank, returns a chunk of that letter, and otherwise it returns this empty segment data structure. And then here's the implementation of the overall algorithm. Define the words in a string. For all of the characters in the string, feed it to process char, thereby mapping it into the rich data space. We used a conjugate data transform here, using this chunk segment data structure. Map each character into that space, hit it with big O+, that does all the parallelism. The result is G, again in this rich data space. We need to do a case on this data space and do the final fix-up, which is very similar to the final fix-up in the sequential algorithm. And then finally, another piece of boilerplate that I've made in earlier examples. I actually need to define big O+ separately up here as an operator and feed it some data structures and stuff that connects it up to the binary O+ down here and also defines the identity value for O+. Okay, so that took about 9 slides. This is a much more complicated algorithm than the sequential version, but potentially big payoff in parallel execution. It's a different way of thinking about organizing code. So to summarize, summations and list constructors and loops all have different syntax, but they're fundamentally the same idea underneath. You generate a bunch of values, you map over them, applying some body function to them, and then you combine the results using some combining operator. Ideally, that combining operator is associative. That entitles you to use a parallel implementation. But whether, in fact, to be sequential or parallel is a separable question, which is what makes these particularly good abstractions. In particular, you can make the decision on the fly rather than statically at compile time. You can make a dynamic decision based on the number of hardware threads available, whether you want to process a particular subtree sequentially or in parallel. Another big idea is you can formulate a sequential loop or finite state machine as successive applications of state transformation functions. So suppose you've got this sequential loop that goes from 1 to a million, and each iteration loop is slightly different, but you can represent that as a function, a state transformation function. There might be a million different such state transformation functions. But if you can find an efficient way to represent those functions, an efficient way to compute compositions of those functions, this step requires cleverness, then instead of initializing S to S naught, and then executing the loop, successively updating the state, instead you can do this computation where you take the state transformation functions, hit it with big compose. Compose is associative, so this has a parallel implementation. And with roughly the same amount of work, but with log time delay, I need a few more minutes, you can compute the composed function, apply that to the initial state, and jump in one step from the initial state to the final state directly. If you need the intermediate results along the way, such as might be produced by a finite state machine that's producing outputs at every step, you simply use parallel prefix with function composition. This gives you a list of functions, and then you map down that list of functions, applying each to the initial state, and that will take you to the correct intermediate state in the computation. I'm going to skip that. Another interesting result is at a paper at the 2007 PLDI. If you could construct 2 sequential versions of a function that is a homomorphism on lists, one that goes left to right and one that goes right to left, there's an interesting crank you can turn to automatically produce a parallel version. And I recommend this paper to you. All you have to do is find the appropriate weak right inverse function, then apply the third homomorphism theorem. See, it's easy. No problem. At the 2009 POPL, there's an analogous result for tree homomorphisms, which is even more elaborate. And I should disclose that the authors of these papers are members of a research group that has had a collaborative research agreement with my group at Sun. But I think very highly of these results. So, to wrap it up, I believe we need a new mindset for multi-cores. Do loops are so 1950s. Literally, Fortran is 50 years old now. And linear linked lists are so 1950s. Lisp is 50 years old now. Java-style iterators are so last millennium. And all of these things are inherently sequential. Even arrays are suspect for a couple of reasons. One is that if you make arrays sufficiently large, up at the petascale, for example, a domain that I have investigated, the hardware is going to be breaking all the time. You can't make memories that big that stay reliable for any length of time. Therefore, you're going to have to provide for memory remapping of one sort or another. There are various mechanisms for doing this involving virtual memory or caches of some sort. All of these, in effect, impose a tree structure on what you thought was linear memory. So what you thought was a big array was a tree after all. It's just that the hardware is hiding that from you. In fact, array indexing relies on addition hardware, which itself is log time. It's extremely fast log time because it uses carry save adders and very clever circuits, but it's still log time. In effect, it's all trees down there. As soon as you say to yourself, first I'm going to set sum to 0, you're already hosed for parallelism. Accumulators are bad. Notice that foldl and foldr, though functional, are fundamentally accumulative in their approach. As soon as you say process subproblems in order, you lose. The great tricks of the sequential past won't work for parallelism. So I think we need parallel strategies for problem decomposition, data structure design, algorithm organization, using this divide and conquer strategy. The top-down view is that you shouldn't split a problem into the first and the rest. Instead, try to split into equal pieces, recursively solve the subproblems, and then combine them. The bottom-up view, which is in some ways a little more interesting, is don't think about starting with a null solution in an accumulator and then repeatedly updating it. Instead, map each input into a singleton subsolution, and then think about how you merge those subsolutions tree-wise. Combining subsolutions is usually trickier than incremental update of a single solution. The programming is actually a little bit harder, but in exchange you get this parallelism benefit. MapReduce is a big deal. Catamorphism is a big deal. I think that language support for helping users to define their own associative combining operators and making sure that they are associative is going to be an important idea in language definition going forward. The fully engineered story is that in practice there are many optimizations you want to use. I've only used binary lists here. Why binary? Well, they don't have to be binary. You can use tree branching factors larger than 2. Clojure uses 64 array trees, for example. We will probably want to optimize representations of the singleton lists and get down the space cost of this redundant representation. Instead of using binary trees, we'll want to use various kinds of self-balancing trees, such as 2, 3, red, black, or finger trees. We'll probably want to use sequential techniques near the leaves. As hardware threads become unavailable, you simply devolve to a sequential implementation of subtrees. Perhaps you want to have arrays at the leaves of these trees. And finally, when you're iterating over integer range, you may want to decide dynamically whether to process sequentially or by parallel recursive subdivision. So to conclude, if you organize your programs and data structures according to linear problem decomposition principles, that code is going to be hard to parallelize. We've had that experience for 5 decades. If we can organize our code and find language support for organizing code in this parallel style, then we can easily execute it in parallel or sequentially according to available hardware resources. This parallel strategy has costs and overheads, quite analogous to those of garbage collection. And these costs and overhead will be reduced over time as we engineer it, but they will not disappear. But as with garbage collection, we will pay those costs gladly in exchange for the automatic management of computational resources, just as garbage collectors automatically manage storage resources. And I believe that in a world of parallel computers of wildly varying sizes, this is our only hope for program portability in a parallel future. Finally, I believe that better language design can encourage better parallel programming, and my advice to language designers going forward is get rid of cons. Thank you.
So I think we have time for a couple of quick questions. If questioners could go to the microphones in the aisle in the middle or on the sides, please. And press the button.
Yes, please press the button briefly and then release it. Don't hold it down while you're trying to speak.
So we like functional programming because it's easy to reason about correctness statically without running programs, and we like parallelism because you can get good performance. So do you think that when you combine the two, you get easier static reasoning about performance without having to do experiments by running your programs?
You stuck something in at the end there that I wasn't expecting. Yes, you want various kinds of static reasoning about the code. This is good. Then at the end you said static reasoning about the performance, which is a different question. I think the business of statically reasoning about correctness is unchanged under this new programming strategy. Statically reasoning about the performance is a very interesting question. I think that it will depend on what we can rely on from our primitives, whether those trees will stay relatively balanced or not. If we can keep the trees relatively balanced so that we can have a simple model of this will be log time, this will be log squared time delay, and so forth, then I think we have half a chance. That will require some engineering. and some theorems. Yes.
You started off with the sorting algorithms, merge sort and quick sort, and you like merge sort because it's structurally inductive, and skimmed over quick sort because it's co-inductive, because it's structured on the structure of the output rather than the structure of the input. Does this work only for inductive things, or does the approach work for co-inductive generation?
That's actually a very good question, something I've just begun to think about in the last week, actually. Thank you for bringing up the terms inductive and co-inductive. I suspect that there is a co-inductive application of these techniques. I haven't had the time or perhaps the mental acuity to figure out what that looks like in a programming language. I simply made the observation as I was preparing this talk, oh, merge is inductive. It's easily susceptible to this familiar notation, which is a very nice property. In fact, I think quicksort is probably the more efficient algorithm of the two. When you go through, if you go through the exercise of coding up both of these in the suggested style, you'll find that the quicksort partition, you choose a single value, and there's this magic oracle in quicksort. You have to choose some value to do the partition. You'll find that when you do the merge, you'll find yourself doing repeated choosing of oracle values. There's more work going on there in the merge sort. But it would be very interesting to try to figure out how to make comprehensions and these big combining operators work from the co-inductive side. I don't know yet what that looks like. So, great question for future research.
So I agree with you about getting rid of cons, but I was wondering why you wanted to introduce conc lists instead. Why not just go the whole hog and use arrays as a language like Nestle does? Because in a way, that then you're saying what you mean, that you just got an aggregate that you're doing an associative operation on. The trouble with conc lists is, you talked a little bit about balance and said you don't know whether you're going to be able to get balance. And also you don't have a good handle on locality. And for big machines, you need locality.
Yes, all good points. Let's see, you've raised several questions. Let me take the locality first. In fact, in the design of Fortress over the last 5 years, we have worried about locality and ways of talking about locality explicitly in the language. The language definition came out of an effort to design languages for high productivity for high-end scientific computations, such as those done by, say, the U.S. national laboratories or large-scale scientific laboratories around the world. And they are interested in managing data locality. I don't have time to go into that story, but it has been a question of interest to us, and you can go look on our website. Oh, it's not on the screen. Fine, go to projectfortress.sun.com, and you can find information about that. As for whether we should think about the conc lists or simply say they are sequences, I'm quite sympathetic to doing most things with sequences, and that is the advantage of the big operator formulation that completely abstracts away the structural recursion. And hides that under the table. And in fact, the details of how you generate an abstract collection from a data structure are something that are separately programmable in Fortress. So in user libraries, you can define various kinds of aggregate data structures, define generators for them, which then entitles you to use the big operator, to use them at the arrow underneath the big operator. And then you also define these reductions, which constitute the big operator themselves, and these things get glued together by the generator reduction formalism within Fortress. Now, there are some kinds of algorithms that don't seem to be completely susceptible to this big operator, hit it all at once, to the big associative operator formalism. You really do want to do the structural recursion. And for that, I think that the conc list formulation still may have a place. I would love to be proved wrong.
I see. So you're really saying use big operators almost all the time, and if you really have to...
And if you really have to, then devolve to doing the binary tree splitting.
Okay,
yeah.
Thanks.
It'd be lovely if we get rid of the binary tree splitting altogether. I'm not quite sure we can do that yet.
I'd like to see those examples.
Yes.
One more.
So you mentioned the need to switch to sequential techniques when you run out of hardware threads, which I guess, in the near future at least, is bound to happen. But switching to sequential techniques doesn't just mean taking your parallel algorithms and turning off the spawning, running them sequentially, because the good sequential algorithm is actually a different algorithm from the parallel one. So that suggests that the programmer is going to need to write both a parallel algorithm and sequential code to use at the leaves. Now, you've told us that automatic parallelization is very difficult, but have you thought about maybe automatic sequentialization? So that you can take the good parallel algorithm and get a nice sequential.
I have, in fact, and in my haste, I skipped over the fine print down here at the bottom of slide 73, noting that a tree can be processed breadth first or depth first or both. Therefore, we might want to use both parallel and sequential strategies and perhaps derive one from the other. It is my experience that I can take a parallel algorithm in this form, and typically what happens in making the sequential version of something, we can formulate it as starting with a null list and then appending the rest of the list to it. We use that null to initialize an accumulator, walk the fringe of the list, and use the binary combining operator, which then can often be optimized because you know something about what its left-hand argument is going to look like. Just as when we determined that MapReduce in the cons case was going to run in linear time, even though we were using append as a combining operator, the append would always run in constant time because we knew something about its left argument. And so I think there is hope for automatically deriving an optimized sequential version from the parallel version by producing optimized special cases of the combining operator for known sequential contexts. Okay?
I think we better stop there.
Thank you very much.